and we would also cover acoustics of vowels and the acoustics of consonants. Okay, so in other words, we will revisit vowels and consonants again, but this time our perspective is not about how our focus is not about how the speaker produced these sounds, but the acoustic properties of vowels and consonants. But you will find that in some cases, we still need to make reference to how the sound is produced to better understand the acoustic properties of the sounds. Okay. Um, so first of all, so today we are going to basically talk about the first topic in acoustic phonetics, which is about the basics of acoustics. I think a very important thing is when we are thinking about acoustic phonetics, we are really thinking of speech sounds as physical objects, right? So because we are more interested in like sounds as physical objects themselves. So what is sound from this perspective? If you think about it, it is a very concise way of defining sound is it is pressure fluctuation that travels through space. That's also why sound is a type of wave. So that's why sometimes we say sound wave, right? And what do we mean by pressure fluctuation? I guess if you still remember, actually, we did remember when we talk about articulatory phonetics, we said that a typical articulatory process will start from pushing air out of your lungs and push that air up through the vocal folds into the mouth or into the nose and eventually out of the body, right? If there's no airflow, there's no sound. Now, if you think about it, having airflow, what does that mean? What does it mean to have airflow? It basically means that there is air pressure difference, right? It's like if you feel wind or if you feel other types of airflow, it's because there is air pressure difference. So this is so now that we're talking about acoustics, you can imagine basically the speaker, when they produce a sound, they produce some airflow. In other words, they produce some kind of pressure differences. And these pressure differences, because what we mean by fluctuation, I think I cannot use, right, if I mean, okay. So what do we mean by fluctuation? Is exactly, fluctuation means that change, I mean some kind of change or variation, right? So for pressure to fluctuate, that means for pressure to change. So in other words, if you think about sound wave, it's basically its pattern of pressure, air pressure change. And this pattern is produced by the speaker when the speaker is pushing air out of his or her lungs and push air through his or her body, right? They produce this pattern of air pressure change. And this pattern can travel through the space because our space, if we are all on the earth, the space is filled with air molecules. So this pattern of pressure change can travel through the space. And eventually, how do we hear sounds? Oh, actually, let me see. Can I try to ask someone here? What about Ka Wen Wang Ka Wen? Are you there? Nope. Okay. What about Li Kawai? Are you there? Yes. Okay. So I'll ask a simple question here. So just now we said that sounds are basically patterns of air pressure change, right? And this pattern of air pressure change can travel in space. So how do you think that eventually, so how does a listener, how do people hear sounds? what organs do you think are involved or responsible for hearing sounds? Okay, so Chen King said ears. Okay. Yes, so ears are, we know, like intuitively, we know that our ears are responsible for receiving sounds, right? So the last part of this class, we will talk about auditory phonetics, like how do people hear sounds? But here, a very simple idea is, because we know that sounds are basically air pressure change. That means in our ears, when we hear, because we are, for us to be able to hear sounds, there must be something in our ears that can perceive, that can sense air pressure change. Okay, so that will actually give you a complete circle. In other words, from what when we began to talk about articulatory phonetics, I said that, from now on, you need to think about speech sounds, not just about what you do with your tongue or your lips. It's really about airflow, right? Now, when we talk about acoustic phonetics, we are going to reinforce that idea. Sounds, it's all about airflow, and airflow is about air pressure change. So speaker produce a pattern of air pressure change. This pattern of air pressure change can travel through space because we have a lot of air molecules in the space. So they will help propagate, they will help spread this pattern of pressure change. And eventually, this pattern of air pressure change will be perceived by the listener, because the listener has some mechanisms in their ears that can perceive air pressure change. Okay, so this actually completes the circle from speaker to listener. This also means that you probably have heard that, like, if you're not on the earth, if you are on the moon, if you're on the moon, and if you just start to talk to someone on the moon, if you start to speak into to someone to the moon, they may not be able to hear you. And that is because on the moon you don't have these air molecules that can spread the pressure change pattern for you. Okay, so to have a complete circle from speaker to listener, you need the speaker to generate this type of air pressure this pattern of air pressure change, and you need some kind of medium like air molecules that can help you spread this pattern. And eventually you need a listener who has some devices in their ears, who has a mechanism in their ears to receive this pressure change pattern. Okay, so in other words, sound is, that's also why we say sound is a type of wave. Okay, speaker is the person who generates this wave. We need air to spread the wave, and we need listener to have the right device to receive the wave. When we talk about air pressure change, remember, the important thing here is it's not just about having pressure, it's about pressure change. So this pressure, we know that any sound wave that most of the sound waves that you can think of, when you look at its signal, you will notice that the pressure is not constant, it changes. And the simplest, okay, maybe I should try to do another type of projecting, so I can use the pen. Okay. Right. So the simplest pattern of pressure change, you might want to think that, does it, if we have, because it's like a change, some kind of change over time, right? So on the x-axis, you have t for time, and on the y-axis, maybe we have p for pressure. Okay, so some of you might think that the simplest pressure fluctuation pattern should just be like this. Okay, but actually this is not the case. Okay, so the simplest pattern of air pressure change will be described as a sine wave. Okay, what does a sine wave look like? If you actually, do you guys know what a sine wave should look like? Yes or no? Have you heard of? Have you studied like sine waves in math or in physics before? If you have, maybe you can type yes to the chat box. Yes. Okay. So maybe some of you have, and I hope you still remember. Let me see. Some of you did say no. No. Okay. If this is the first time you hear about sine wave, I guess for now, have you ever seen like does this type of thing look familiar to you? This is what like a sine wave, could look like. So the idea is, if you look at a sine wave, the idea is the change over time. So there is definitely change in pressure over time, right? Like at any point of t, you get a slightly different p. But one feature is that this type of change is very smooth. So you don't have any abrupt changes. It's very smooth. If I'm looking at two time point, like T1 and T2, like the difference in the difference in pressure will not be very big. Okay, so if I get the reading on the y-axis, the difference between these two time points in terms of pressure wouldn't be very large. So the idea of smooth is that there's no sudden pressure change. It's a very smooth change. And the second thing is that you notice that this type of pattern will have you will have periodic change, meaning that you can see there is like a change pattern that will repeat itself. So for example, here we have the pressure goes up when time increases, right? And this point is probably where you get the maximum pressure. And then the pressure starts to decrease, pressure starts to go down, and then it go down further, and then it reaches the minimum pressure point. It reaches the point where pressure is the lowest, and then it goes up again, okay? And then when it comes to the this like 0 point, you notice that it will repeat basically what has already happened. So you have this idea of, I didn't draw this very well, but in theory, a sine wave is a type of pattern that will repeat itself. Okay. So if you have never studied sine wave before, I don't know whether this will help you, but so you can think of this. One way to illustrate. So where do we observe sine waves? Oops. Let me see. I see a chat message. It's a bit. Oh, okay. So hopefully, yeah, I mean, it'll be great if you all have seen something like this you must have learned this in your math class before in high school. So one way to illustrate a sine wave is to think of the swinging of a pendulum. This means that, like if you imagine if you on the ceiling surface, you hang a string. At the end of the string, there is a ball or something with weight attached to it. Now, if you move this thing to, you can imagine if I hand this weight here, right? And if I lift it to this position, if I move it to this position, and if I let go of my hand, and then it'll start to do like left to right, right to left, this type of motion, it'll go between left and right, right? So it'll start to do this very regular movement. And if we don't consider the attrition from the air, this can be a type of movement that never stops, right? So this can really go on forever. And if we have a way to plot, now you have to imagine this is like the max left position, right? Max L, the maximum position you can reach on the left, and this is the maximum position you can reach on the right. So if we have a way to plot how this motion will look like over time, you can imagine if there is like a piece of paper that I put under this motion device, and this piece of paper will move when at a very constant speed when time goes by. So I can plot on this piece of paper the position of this ball in terms of how far left or how far right it is. The middle point is center, right? So here you have C. So if you are able to plot the trail of this motion over time, you will see this type of curve, meaning that we know that this ball maybe it starts at let's say it starts at the maximum right position, and then over time it cannot go any further on the right, so it will slowly go back to the center, and it will slowly go back to the max left position, and then when it reaches the max left position it will come back. So this would also be a very smooth motion. And if you think about it, when it reaches the max right or the max left position, the speed of this motion will become zero. So that's why you have these points here where locally it looks pretty flat, because these are the points where the ball needs to like reverse in direction. So there will be a brief moment where the speed is really zero. So you see these like flat, locally kind of flat areas. And when the ball is passing through the midpoint, passing through the center, this is where you see maximum speed, right? So that's why you have these areas where it looks very steep. Steep means that the ball moves. The ball will move a larger distance given the same amount of time. So you see these like steep areas around the center, because this is where you get maximum speed. So overall, this helps you kind of understand why it's this type of curves when you are observing a pendulum motion. And this type of curve is what we call a sine wave. Earlier we said one feature is that it's smooth everywhere, so you don't get like sudden changes. And the second feature is that it's regular. So you see the same pattern repeating over and over. And if you pay further attention, you will see points like on the two ends where locally it's very flat, and also points in the middle where locally it's quite steep. Okay, so you see, if you combine all these features, they are features of a typical sine wave. Of course, you can get sine waves that look slightly different. Maybe they can be more flat. Okay, it's like you imagine you can sort of stretch this curve like along the x-axis, or you can compress it along the y-axis, or you can stretch it along the y-axis. But overall, this is the shape of a sine wave. Right. So if the sine wave, if air pressure change also follows a sine wave, meaning that if we have a type of a sound where that can be described as following a sine wave in terms of air pressure change. So you also have like a max pressure point, a minimum pressure point. Over time, this pressure will fluctuate between max pressure and minimum pressure, and it will also go through like a 0 point or maybe a midpoint, a center point. If this pattern also follows a sine wave, what will the sound like? Okay, so here I'm going to show you what the sound will sound like. So can you all hear the sound? How would you describe the sound? Does it sound like something that humans can produce? Do you think it sounds like this is produced by a person? Does this sound like it's produced by a person or a computer? A computer. Yes, it doesn't sound. Oh, someone said that you cannot hear the sound. Can you all hear the sound? Let me see. I think this is almost. Okay, can you all hear the sound? Does it sound like it's produced by a computer or a person? Winky said that you. Computer. Most of you said computer. So if you still, I'm going to play this one more time. If you still cannot hear it, I mean, you have the slides. So slide 6, you can also play the sound on your, if you download the slides. So this is a sound that clearly we all agree that this is a sound that's produced by a computer. It doesn't sound like a sound that's produced by a human, because this is right. Because this is a sound that I synthesized on the computer to be a perfectly to have a perfect sine wave in its pressure change pattern. We know that humans are not perfect, so nothing we produce, we cannot produce a sound that is perfectly a sine wave. And not only is it impossible for humans, it's also impossible for animals, or for like any sound that you hear, like car sounds or the sound of wave or the sound of the rain. So in general, like naturally produced sounds are not going to be so perfect. They're not going to have a perfect sine wave. So these sounds that do have perfect sine waves, they are all synthesized by computers. Now, the second thing is, now we know that this sound is synthesized by a computer. How would you describe the sound? I mean, we know that it's not a human-produced sound, so I'm not going to ask you if it sounds like, like what's the place of articulation or anything like that. But how would you describe the quality of the sound? For example, does the sound have a pitch? Do you think it has a pitch? Does the sound have, what is pitch? We talk about like tones and stuff when we talk about super segmentals, right? We talk about pitch. So do you hear pitch in the sound? Like if someone asks you do you think the sound has a high pitch or a low pitch, given your experience with sounds? Like, do you hear any pitch in the sound? Someone said, someone said it has a low pitch, okay, and someone said no, okay. Let me see. I think I have more examples. Here. No. So, what about other people? So maybe I will ask you a different question. If I ask you to imitate this sound, we know that this is a computer-produced sound, but can you imitate the sound to it does have a pitch, right? So one way you know that it has a pitch is it's something that you can hum, if you do like, can you do a sound that is very similar to this pitch? So I'm going to ask, I think Eric, because you said that you don't hear a pitch, right? Eric Shi, are you there?
Yeah, I'm here.
Okay, Eric, can you hear the sound?
Yes.
Okay, now I'm going to play it one more time. Can you try to say to be like very similar in pitch to the sound, to imitate it?
Sure. Something like that.
Okay, good. So that actually tells you if you can to approach it in pitch, that actually tells you that this sound does have a pitch, right?
Yeah.
Okay, now Eric, do you think the pitch of this sound, does it change?
No.
So it does. You think the pitch doesn't change? It's constant, right?
Yes.
Okay, good. So I think we all can agree with Eric on this one. this sound does have a pitch, and it doesn't change. Okay, this is a constant pitch. So this sound, when you hear it, it does sound very simple because it's generated by a computer. It sounds kind of pure, and there is a pitch, and this pitch doesn't change. Now, try to remember what this type of sound like, because these are the simplest sounds. Okay, they are the most simple sounds. What do we mean by most simple? Because if you look at the sound signal of the sound, later we will talk about how to look at sound signal. But in general, when you look at the signal of the sound, you will see this type of sine wave. Okay, it's not completely flat. There is still pressure change. So you don't see a flat line in the sound signal of this type of sound. You see sine wave. But this is already the simplest type of pressure change. And the quality of the sound will be like this. It has a pitch, and this pitch doesn't change. Okay, so in fact, this is the sound that you just heard. It's a sine wave of 200 hertz. So I synthesized the sound to have a pitch of 200 hertz. I remember someone said earlier that this sound seems to have a low-ish pitch. Okay, obviously high or low depend on your experience with sound, but I can actually tell you that the pitch of this sound is 200 hertz. And if you still remember, if you still remember, we kind of talked about these things when we talk about pitch in like speech sounds, like sounds that are produced by humans, right? So we kind of, I think we did mention that hertz is this unit for frequency. So when you say 200 hertz, 200 hertz means that there is a pattern that repeats itself 200 times, right? Meaning that we know that this sound, the air pressure follows a sine wave, and this sine wave contains many repeating cycles. So for this sound, I set it so that these cycles you see here, we can probably trace this. Here we see one, actually it will be more like from here to, okay, sorry. So we have like 1 cycle, 2 cycles, 3 cycles, 4 cycles. So it's like a little bit more than 4 cycles. But this sound wave actually has a frequency of 200 hertz, meaning that in every second, it repeats 200 of such cycles. Every second, you see this cycle repeating itself 200 times, okay? So it's, this is actually the first acoustic property that we will talk about. When we describe sine waves, we can talk about its period, like, and frequency. Both are about basically the pitch of the sound, because a sine wave is so simple, right? When you listen to it, you notice that there is a pitch. This pitch can be high, can be low, and this pitch is something that we can actually calculate. And this pitch is constant, it doesn't change. How do we calculate the pitch of a sine wave? We either count the frequency of the sound, like the number of cycles per second in the unit of hertz, or you can ask a similar question like how long is each cycle? Because if the pitch of the sound is 200 hertz, that means 200 cycles per second, then each cycle will have a duration of 1/200 second, right? So these two are the inverse of each other. So, similarly, if you already know that we're talking about a sine wave where the duration of each cycle is 0.2 seconds, then, if you need to know what's the frequency of this, then each second you can have 5 cycles, right? So the frequency will be 5 hertz. So these two will be the inverse of each other. And they both describe, they're like the two equivalent ways of describing the pitch of this sine wave. Apart from that, we can also describe amplitude. Okay, so amplitude or loudness, basically how loud the sound is. This depends on, if you look at this really depends on like how high or low the max and mean pressure can go. So you can imagine if this wave can really go very high, if max pressure can be very high, mean pressure can be very low. So if the difference between max and mean is very big, then this sound will be very loud. So in other words, when you look at the signal of a sound, the greater the change on the y-axis between max and mean pressure, because we already know that it's a periodic, it has these like repeated cycles. So you can describe how fast this sine wave repeats its cycle. The faster it repeats the cycle, the higher the frequency. So you will hear a higher pitch. And you can also describe how loud the sound is. And that basically depends on the difference between the amount of difference between max pressure and mean pressure. And the louder the sound is, the more energy there is in the sound signal. Okay. So the next thing we're going to talk about is really this idea of periodic versus aperiodic sound. A periodic wave, just now we talk about sine wave. So sine wave, as we said, is the simplest type of sound wave. It has its own shape, right? So when you see the shape of a sine wave, you can tell, oh, this is a sine wave. And a sine wave, it does have these repeating cycles. If a sound wave has repeating cycles, we will say this is a periodic wave, okay? But apart from simple sine waves, there are also other waves or other possible pressure changing patterns that are periodic, even though they're not sine waves, okay? So for example, if you look at these figures here, there are 4 figures here. Each figure represents a certain type of pressure change. So each figure represents a sound signal. On the x-axis, you see seconds, right? So the x-axis, the horizontal axis, is time. Each figure shows you a window between t equals 0 and t equals 0.05, so 0.05 second. And on the y-axis, you see pressure, okay? So you have plus pressure, like pressure, positive pressure, negative pressure, and 0 in the middle. So each figure shows you a window between t equals 0 and t equals 0.05 second, and how air pressure changes over time. So here are 4 different sounds, right? So just by looking at it, okay, we won't be able to hear these sounds, but what we're looking at is the sound signal, which is the pressure changing pattern over time. So if we just look at this, like the first figure here, does the first sound signal look periodic to you? Yes or no? Okay, some of you said yes. Okay, I'm waiting for a few more answers. If we look at the first figure here, does the sound signal look periodic to you? In other words, do you think you can see something repeating here? Yes, okay. Now, if you think I agree, this looks periodic, okay? If you agree that it's periodic, can you tell how many cycles there are or how many times this pattern is repeated within this window of 0 to 0.05 second? Like roughly, can you count how many cycles? Some of you say 9, okay, 9 cycles. Some of you say 8, okay? So we can count together, right? Let me going to use my, okay. So if you are with me, you're probably counting like, if I start here, I have 1, 2, 3, 4, 5, 6, 7, 8, and like a little bit more than 8, right? So yeah, so it's probably like between 8 and 9. So I agree there. If I'm just like looking at the signal with my eyes, I can see something that's repeating, and it's repeated itself like 8 or 9 times in this window. Now, when you look at this signal here, do you think the cycles are exactly the same? So there are like so we said that there are 1, 2, 3, 4, 5, 6, oh, very ugly, 7, 8, okay. Are these 8 cycles exactly the same? No, okay. So they are not like, just now when we talk about simple sine waves, every time the cycle repeats itself, it's really exactly the same. But in this case, we have these cycles that we think look very similar to each other, but they're not exactly the same. Okay, so this actually is a very typical signal of a real, like a human produced sound. This is probably a vowel. Okay, so this is a very this is really a signal that human can produce. You do see these like repeating cycles, but these cycles are not exactly the same. Why? Because we're humans. We cannot really do anything. We cannot do anything that's like like if you ask yourself to repeat a motion, even if it's a simple motion, it's not going to be exactly the same every time you do it. Okay, so yes, so the first figure here, we will still say that it's periodic, but even though it's not like complete, it's not perfectly periodic, but we can definitely tell that there is something repeating. And the first figure here, is this a sine wave? It's clearly not a sine wave, right? It's repeating itself. It's not perfectly repeating itself. At the same time, it's definitely not a sine wave, okay? Now, what about the second figure here? If you look at B figure, this one, is this periodic or not? Do you see some pattern that's repeating itself? Like like in the first one we clearly see it repeats something 8 or 9 times. Do you see anything repeating in the B figure? No. Okay. Yes. So I cannot tell what's repeating in the B figure. At least if I'm just looking at this now, I don't see anything that's repeating itself. It all seems to be just like random. There is pressure change for sure. Okay. You see these like vertical bars. And these changes, if you look at it, these changes seem to be kind of abrupt, right? It's abrupt. That's why you see, like, you don't see at least in the figure A, you can see these continuous lines tracing pressure change, right? But in B, they look like vertical bars, meaning that there are probably some very abrupt change. Like you go directly from maybe +10, and then the next moment it's -10. So it's like a vertical bar. You don't see curves. If you don't see curves, you see vertical bars. That means there are very abrupt changes. So B is not periodic. What about C? Do you see something repeating in C? Do you see some patterns that's repeating in C? Yes or no? Okay, some of you said yes. Again, we know that this is marginally yes. Okay, so again, we know that this is a situation where, maybe we do see something. If you do see something repeating, how many times does it repeat itself? How many cycles do you see? Also 9, okay, maybe 8 or 9. So yeah, so it's kind of similar to A, right? So if you start to trace this, I'd probably be like, oh, I think maybe like from, maybe from like here to here, I get 1 cycle, and then here I get second, and then 3, 4, 5, 6, 7, 8, like something between 8 and 9. I do see something repeating itself, okay? But they are also, every time it repeats itself, it's not exactly the same, okay? So let's say we still say this one is periodic, this one is periodic, okay? B is not periodic. What about the last one, D? Is D periodic or not? The last one, D, periodic or not? No, we don't see anything repeating. Actually, you notice that D is also the only signal where in this part, we don't see any pressure change, right? The line is flat. And in this part, we also don't see any pressure change, line is flat. Meaning that this sound, in this window from t equals 0 and t equals 0.05, we only will hear something in the middle part, okay? There's no sound here and there's no sound here. So this is the type of sound where you kind of have some kind of silence at first, and then some silence afterwards, and then some kind of sound. And in the part that does have sound, there's also no periodic cycles, okay? So between A, B, C, D, we would say that A and C are both kind of periodic. They are not perfectly periodic, and B and D are aperiodic, meaning that they don't have anything that repeats itself regularly, okay? So actually all these four are sound signals of like speech sounds that human can produce. So humans do produce some sounds that will look like A and C, where you do see some kind of periodicity, like some pattern repeating itself. But because we are humans, so when we repeat something, it's never like a perfect repetition. We also produce sounds that will look like a B and D, which are just not periodic waves, okay? Maybe I will ask an extra question, okay? So now let's just look at A. Between A and C, A is probably more periodic, okay? Let's look at A. So we already agreed that this is periodic, A is periodic, okay? We know that there are 1, 2, 3, 4, 5, 6, 7, 8. Let's say eight cycles here, okay? What is the frequency of the sound signal in A? In other words, how many cycles will be repeated in 1 second? Someone said 16, okay. Okay, any other guesses? Any other results? 16 or 160? So what we know here is you see the signal repeat itself 8 times in a window of 0 to 0.05 seconds. So in a window of 0.05 seconds. The question is how many times, how many cycles will be repeated in 1 second? Okay, so Iris said 160. Any other answers? Any other answers? Do you all agree? Okay, Dialogue also said 160. Okay, so so you all agree that it should be 160, right? What about Man J? Do you also agree? Oh, are you there? Yes. Oh, you're here. Do you agree that do you also think that it's around 160? You don't know how to count, okay? So so this is actually, how about Iris? Because Iris, you said 160, right? Are you there, Iris? Yes, okay. Iris, can you do you have, if you have a mic, maybe can you explain to us, like, how did you count? How did you get 160?
Hi.
Uh-huh. Yeah.
What I did was first, because for the periodic wave, it was from 0 to 0.05 seconds. So to make it 1 second, we have to repeat the cycle for 20 times. Because to make the seconds into 1, it has to be 0.05 times 20, while there should be 16 cycles, no, 8 cycles repeating in 0.05 seconds. So if we times 20, it should be 160.
Yes, that's great. So that's a very basically, like this is just a simple math. So if you are, if someone asks you, okay, if you look at this A figure, and can you figure out what's the frequency of this sound? Then you look at the A figure, you notice, as Iris said, this figure only shows you a window between 0 and 0.05 second. That's 1/20 of a second. If you are not sure about that, you can just do 1 divided by 0.05, right? And in this very short window, you already see 8 cycles. So you can imagine, if you have a window of 1 second, you will see how many cycles. That should be 8 times 20, because 1 second is 20 times of 0.05. So in other words, if you are able to see a window of 0 to 1 second, you expect to see this 8 cycles times 20, right? So you expect to see at least 160 cycles. Now, I see Ethan responded. Now, Ethan, if you agree with Iris and you think the estimate for this sound signal is really the frequency is 160 cycles per second, so it's 160 hertz. Hertz is this unit for like number of cycles per second. Now, Ethan, and we already know that this is probably produced by human, right? Do you think this is a guy or a girl?
It's a guy.
It's a guy. Why?
Because 160 hertz is a low frequency.
160 hertz is pretty low for human voice, right? Yeah. So how high do you think female voice should be?
As I remember, I think it's somewhere around A4 is 440, and I think it's somewhere around 400 to 500. It's a normal female voice.
Okay, so 400, 500 is probably a bit too high. I agree with you that this 160 hertz is more likely to be a guy's voice. A female voice is probably like in the 200s, so probably up 200. Yeah. I guess 400, 500 if they're singing, because singing, of course, you may use a higher pitch range. Maybe if they're singing, they could be like higher pitch. But if we're just talking about like conversational voice,
right.
Female voice. Yeah. Okay, good. So thank you, Ethan. So in other words, like given our knowledge of acoustics, you can actually read quite a lot from just a very simple figure without even hearing the sound. If we just see a figure like A, we will be able to tell, first of all, this is probably not computer generated voice, because we see it, well, first of all, we see something repeating itself. We see it's a periodic wave. We also see that it's not perfectly periodic, suggesting that it's probably not produced by a computer. It's probably produced by humans. And we also can count the number of cycles, right? There seem to be 8 cycles here, and in this window of 0.05 second. So we can estimate the frequency of this sound signal by figuring out how many cycles will be repeated in 1 second, if 8 cycles are repeated in 0.05 second. So we estimate the frequency to be 160 hertz. And because 160 hertz is a typical frequency for male speakers normal conversational voice. So we can also guess that, this is probably produced by a male speaker, okay? Now, this is already quite a lot of information we can get just from a simple figure of a sound signal without listening to the signal. Later on, when we talk about the acoustics of consonants and vowels, we will be able to see more. We will probably be able to see this looks like a vowel. Okay, so this is actually you only need very simple acoustic concepts to be able to read a lot of information from this type of figures. Okay, now I think we can move on. So now we are going to talk about something that's slightly more complicated. Okay, so if we know that, so whenever we say simple wave, okay, whenever we say simple wave, we basically mean sine wave. So when we talk about acoustics, what we mean by simple is sine wave. Sine wave is the simplest sound wave. Okay, but this strictly, or when you say pure tone, means that it's constant, that the frequency F is constant. Okay, so pure tone means that there's only like one tone and it's a constant tone. So strictly speaking, this type of like pure tone, simplest sound wave, the sine wave, they do not occur in nature. So that's why we all agree when we hear that sound that I played earlier, the 200 hertz sine wave, it doesn't sound like anything you will hear produced by humans or by animals or by cars or by rain or anything. It doesn't occur in nature. Nothing in nature will be like pure or perfect, right? So what we do observe in nature more likely are things like A and C. So we do see these like periodic waves. They're not perfectly periodic, and they definitely look more complicated than a simple sine wave. So what we see in nature, especially in speech sounds, are more likely non-sinusoidal, meaning that it's not sine wave. Okay, so it's non-sinusoidal, but it is still periodic. Okay, so we do have a lot of these things when we look at speech sounds. But the good thing is that all these non-sine wave periodic sounds, they can always be broken down into a set of sine waves. Okay, and a quick way of doing this is if you just look at the signal in A, it's definitely not like this, right? It's not a simple sine wave. But you can see that there are some like peaks and alleys that repeat itself. So you can imagine this complex thing, this complex signal here, it's really the result of adding a number of sine waves, maybe of different frequency and different amplitude. Adding them together, you will get something complicated. So we're going to show this idea in the next slide. Okay, so the next slide is an example of getting a complex wave. Complex means it's not sine wave. Okay, sine wave is simple. Anything that's not sine wave is complex. This is complex, but it's still periodic. Okay. So here I have, what do I have here is, what do I have here are, on the left side, I have two simple waves, two sine waves. One is at 200 hertz. We've already heard this. I'm going to play this again. Okay, make sure that volume is max. So we've heard the sound again. And here I'm also showing you the signal in the window of 0.01 second. I'm only showing you like 0.01 seconds. So you see it is a perfect sine wave. Now the next, the lower signal is also a simple sine wave. So it's also a pure tone, but it's at a higher frequency. Okay, should all be able to hear this. And I'm also showing you a window from t equals 0 to t equals 0.01 second. So when you compare these two, right, clearly you see they are both sine waves, but this sine wave is faster. So you see more cycles in the same time window because this one has a higher frequency. Okay, so I'll play this again. This is the lower frequency, 200 hertz sine wave. This is a 400 hertz sine wave. Now, if I add these two signals together, what would it sound like? If I'm adding these two signals, literally, I'm also showing you here, what does it look like when I add them together, right? Literally, so how do I get this curve? I'm literally just adding up, like this one at the same time at time equals 0. This one is 0. This one is also at 0. So when you add them together, it's also at 0. And at every point, I'm kind of just like adding their readings on the y-axis together, so you get something like this. And what does this sound like? So when I add these two together, you should be able to hear that it definitely sounds different than these like simple waves, right? These two, the reason why we also can say that they're pure tone is you only hear one pitch, right? There's only one pitch. When you put the two together, it becomes more complex. You should be able to at least hear that it's definitely more complex than pure tone. And if you really pay attention, you should be able to hear that there's like more than one pitch going on, okay? If you are musically trained, if you have had a lot of musical training, if you have studied musical instrument or singing, maybe you will be able to hear, oh, I think there is this pitch and this pitch. Maybe you'll be able to separate the two pitches. But even without musical training, you should be able to hear that this is definitely a more complex tone than the two pure tones. This is the result of adding the 200 hertz signal and a 400 hertz signal together. And this is what the sound pressure change pattern will look like. So you notice that, for example, there is still some similarity between this complex signal and the two simple signals, right? They are all 0 at they are all 0 at y is 0 at t equals 0 because it's 0 at the same points at both simple waves. And also in the midpoint, when t equals, I guess, 0.005, right? The pressure is 0, pressure is 0 here, so pressure is also 0 here. And when t equals 0.01, pressure is 0, pressure is 0, pressure is 0 here. And all the other points in the middle is the result of adding the y reading in the first signal and the y reading in the second signal, okay? So this is, in other words, when you add two simple waves together, you get something that is still periodic, but it looks more complicated. It doesn't look like a simple sine wave anymore. So you can imagine, if I add more things, if I add, instead of two simple waves, 3 simple waves, 4 simple waves, or 5 simple waves together, I will get even more complicated looking complex waves as a result. But this complex wave will still be periodic. Like in this one, it's complex, but it's still periodic. We see 2 cycles repeating, right, in this window of 0.01 second. Okay, so that is this idea of complex wave. So, okay, so we know that a complex wave, actually maybe we should, is there any question at this point? So far so good? Everything okay? Okay, so why don't we take a break, because it's it's 10:34 now, so let's take a break and come back around 10:40.